Okay, today we're going to focus on 4 very specific waveforms. These are taken from the list of 12 very primitive drawings that we looked at last day when we were talking about waveform symmetries. So what I want to show you today is that we can take the drawings themselves and translate them into functions. So we're going to write down the equations that correspond to the waveforms. For the purpose of the lecture, I'm going to focus on waveforms 1, 7, 9, and 5. You can see that each piece of the periodic waveform uses a straight line representation. So what does this mean? This means that every equation that we write will be of this form. You might be very familiar with the equation y equals mx plus b. And that would have x as the independent variable and y as the dependent variable. But you can see in all of our drawings, we're using time as our independent variable and voltage as our dependent variable. So we end up with this. This suggests that voltage is a function of time. M here, of course, will be the slope. Normally B is the y-intercept, but of course in these drawings, it will be the value of the v-intercept. Okay, so where does the straight line cross that vertical axis? All right, let's look at the first drawing here. Notice that what I've gone ahead and done is included where one full period would end. So for this waveform, we have one positive half cycle and one negative half cycle. This, of course, is a square wave. Now, this means we're going to be breaking up our time domain into 2 pieces. So we're going to be considering one straight line for the first half cycle, and then a second straight line for the second half cycle. For this first half cycle and this second half cycle, we are going to have 0 for our slope because these, of course, are horizontal lines. So each piece there, so I'm going to write here M1 is 0, M2 is also 0. So the slope of the first line, the slope of the second line. What are the values of B? This first line intersects the vertical axis at a height of Vmax. The second line, if extended, would intersect the vertical axis at a height of negative Vmax. So to get the correct equations, we just substitute these values now into the equation. So it'll look like this. We're going to have V at t equals Vmax for the first half cycle. And then V at t equals negative Vmax for the second half cycle. Okay, so this is information about the domain. All right, let's go ahead and look at the second one. So this is drawing 7. Again, the numbering you see is referring to the numbering on this page with 12 waveforms. So I've taken this very primitive sketch and drawn it again here. I know to mark one full period length when the waveform begins to repeat again. Okay, so in number 7, this represents one full period because then you can see this is going to start repeating. The pattern will repeat. So I've drawn it like this for you again, showing one full period. Now, it is one straight line, one continuous straight line from 0 to capital T for number 7, which means we are not going to have to break our domain up at all. So we will have one equation only for the full period. All we have to do, therefore, is work out what we'll be using for M and what we'll be using for B. Okay, for M, you might want to do this by taking 2 points on the line. For example, this point right here has time 0 and voltage negative V max. While this point up here will have time capital T and voltage positive V max. And from there we can calculate the slope. The slope will be the rise over run. So we can do V max minus a negative V max. That would be our rise. And the run would be capital T minus 0. So what does this give us? This will give us 2 times V max over capital T. So this represents the slope of the straight line. It'll be substituted here. Now, what about the value of B? The value of B can be read directly from the graph. This straight line intersects the vertical axis at negative V max. So we simply substitute this M and this B into this equation, and we get the following. 2 V max over capital T multiplied by little t, and plus B becomes minus V max. Okay, great. So we're going to go on to the next one. Here we go. The next one is problem 9. There is no repetition in the period until here. We have 1/2 cycle given by this straight line. The second half cycle is 0. So we certainly do have to break this one up. So we'll have 2 pieces, first half cycle, second half cycle. So this says time is between 0 and half a period. This says for time between half a period and 1 full period. That's what the notation here means. Okay, so we're going to come up with the 2 equations that correspond. Now, we already said that for the second piece here, we have nothing but 0. So we might as well write that V at t equals 0 when time is between capital T over 2 and t. So now I'm only missing the other voltage equation represented by this straight line here. Okay, so in coming up with the slope for number 9, again, I might want to use 2 points that are on the straight line. So one point is the origin. So that's time 0, voltage 0. The second point, I'm going to use the very top of this triangle here. Okay, what is the time here? If that's capital T, then the time here is capital T over 2. What is the voltage here? Well, we're at the top of the triangle, therefore the voltage is Vmax. Okay, so this is the point 0, 0. This would be the point capital T over 2, comma, Vmax. From this, we can calculate the slope. So rise over run. So Vmax minus 0 over T over 2 minus 0. So we get Vmax divided by T over 2. And this is the same as 2 Vmax over T. So when you divide by capital T over 2, it's the same as multiplying Vmax by 2 over T, multiplication by the reciprocal. So this is the slope corresponding to the first half cycle. All we need now is to take note of the value of B. Again, where does the straight line cross the vertical axis? At 0. So the value of B is 0. So to fill in right here, all I need to do is substitute this slope and this intercept into this equation. And when we do that, we will get this. V at T equals M, which is 2V max over capital T. We have to multiply it by little t, and it would be plus 0. Okay, so now we have the equation for the first half cycle, followed by the equation for the second half cycle. Okay, we are going to do one more together. So let's have a look at the diagram. Here it is. So I'm hoping you can tell me that these are two different straight line pieces which will require us to handle our equations this way. So we will have one V at T expression here and a second V at T expression there. Okay, now let's work on coming up with those expressions. So for the first piece here, we're going to actually have exactly the same first piece as we did in number 9. Okay, because here again, this would be capital T over 2. For the first piece, we have the same slope and the same intercept as we did here. So the expression is going to be exactly the same. Okay? But for this piece, we will definitely have some differences. Okay, what is the main difference for the slope? Using symmetry for the diagram, you should see that the slope here will be the exact negative of the slope here. And that means we can use negative 2 Vmax over capital T for the slope. So that's the slope. We have to multiply it by little t, and then we're supposed to be adding the intercept. Now, simply because this line does not currently touch the vertical axis does not mean that its intercept is 0. We would have to actually picture the line extended to see where it would hit that vertical axis. And using symmetry, we should know that it will hit at exactly 2 times Vmax. So this will be plus 2 Vmax. Okay, so again, the same magnitude of the slope, but with a negative orientation. The line is falling to the right instead of rising to the right. And double the value of B. Okay, I hope that you followed that lesson fairly well. What I'd like you to do is try the very same analysis with these 4 waveforms. So waveforms 3, 6, 8, and 4. Now, a couple of hints before you get started with that. Question 3, you're going to have to do it in 2 pieces. Question 6 should require only 1 equation. Question 8, if we tried to start from 0, we would have 1 piece here and a second piece here. However, if you just switch your starting point to negative t over 2 and your ending point at t over 2, that of course is 1 full period, you can do it in 1 piece, 1 solid straight line from here to here. So I'd like you to do it that way, okay? Should have just 1 equation and time between negative t over 2 and positive t over 2. Similarly, when you go and try problem 4, if you start here at 0, you would have to do 1 piece, 2 pieces, and a 3rd piece. Because again, you need all parts of this cycle. However, by shifting our starting point to negative t over 4, negative 1/4 of the period, you will do it in 2 pieces. So from negative t over 4 to positive t over 4, 1 straight line. Then from t over 4 to 3t over 4, the second straight line. So you will break this one into 2 pieces, 1 and then 2. Okay, give those a try. I will post the answers for this as well. Okay, thanks for listening. Bye now.